All right, this is Miss Straughter. We are going to continue what we started in our notes yesterday. We're just going to do it with play posit. Just to remind you, you're filling in the blank for the things that you see in red. Now, because this is a video, you are able to stop and play as needed. So anytime you see the color red, make sure you stop, look at your notes, fill in what's on the screen, and then continue to play. Keep in mind there are going to be questions embedded throughout the video that you will pause and have to answer as you go. This play posit is going to count for a grade. You have the notes in front of you. You have the ability to replay a section. So you need to use that to your advantage. All right. So like I said, we've already started these notes, so we're continuing, but before we continue, I'm going to just review a few things first. First off, title again is Convection in the Atmosphere. That's what we're focusing on. Remember, our goal is students will develop and use models in order to show convection patterns and how they flow due to uneven heating from the sun, highlighting that heat energy drives the movement of matter in the system. We talked about our atmosphere and how it's just a mixture of gases that surround the Earth. We discussed what atmospheric heating is and how our atmosphere absorbs energy from the sun and how that energy can go to the atmosphere, land, and water, and it is changed into thermal energy. We briefly went back over what heat transfer is and how it's moving from a warmer object to a cooler object. We understand that there are three ways that heat can move: by contact, which is conduction, when the objects are touching, by radiation, when there's electromagnetic waves, and by convection, which is through a fluid. We've already discussed that convection is heat transfer within a fluid, but what's important again, like I said, is that circular pattern that happens with convection, that warm rising and that cold sinking. We discussed how radiation from the sun and conduction from the air molecules heat air, and as that air becomes heated, it becomes less dense and rises. That cool air is denser, so it sinks. As that cool air sinks, it pushes that warm air up. The cool air is eventually heated by the Earth's surface and begins to rise again. And we call this a convection current. We drew a convection current. And again, as this air, and I'm writing in red, as this air rises, this warm air rises, it can only get so high before it starts to cool off again. And as it cools off, it becomes more dense and starts to sink. And that sinking air replaces that warm rising air, which gives us our convection current. Differences in temperature of the atmosphere result from the amount of solar energy that's absorbed. And so we've discussed how warm air is less dense than cold air, and that's because it's absorbed more thermal energy. It is moving faster. The particles are spread further apart, and so it has lower pressure. That's why it's able to rise. It's less dense. Whereas colder air, it's moving a lot slower. Those molecules are moving closer together, and that's why it's more dense and it sinks. We have those differences in air pressure, again, because the Earth is unequally heated by the sun. Can't stress this enough. You need to know that. We have differences in air pressure because the Earth is unequally heated by the sun. And so we discussed how the equator is receiving more direct solar energy and is warmer, and how your poles receive more indirect solar energy and is colder. We watched this video which discussed how that differential heating plays a part. And then we drew this picture. Again, I want to emphasize that there is more direct sunlight at the equator. The sun's rays don't have to travel as long as a distance. It's covering a smaller area, which means it's going to be more intense. Shorter distance, smaller area, more intense thermal energy at the equator. Whereas at the poles, that sun's energy has to travel a further distance. Because the Earth is tilted, it has to cover a greater area. Again, that indirect heating, which means since it's covering a greater area, it's being spread more thin. That thermal energy is being spread more thin, which means it's not as strong. So direct solar energy, indirect. Now, this is the part where some of your classes either stopped, some of you were about to start this one, or some of you were in the middle of completing this one. Either way, remember, whenever you see red, you're responsible for stopping the video and filling in your notes, because that is part of your grade, the notes as well as your responses to the questions. So look at your notes, see where you are. Air rises at the equator and sinks at the poles. And as we already discussed, air at the equator is receiving more direct solar energy. It's hitting it it's coming a shorter distance, and it's hitting a smaller area, so it's going to be more impactful, more intense. So it's receiving more solar energy. The air is warmer and less dense. The warm air is rising, creating areas of low pressure. That warm air flows towards the poles, because again, that's what heat does. It goes from hot to cold. So that warm air is going to rise and start flowing towards the poles. Once you get to the poles, or once it's on its journey to the poles, that air is going to start to cool off. And as that air cools off, it's going to become denser. And then that cold air is going to start to sink, creating areas of high pressure. And that cold air is going to travel and flow back towards the equator, completing that convection cell. So the big question is, why do we have wind? What is convection's part in the reason we have wind? Well, here goes that sentence again. The Earth's uneven heating by the sun causes differences in air pressure. Wind is the movement of air because of these pressure differences. It's all about the differences in pressure. If air were the same pressure, there's no reason for it to flow from here to there. But because they're different pressures, which again are different temperatures, that air, those air particles have to move in those convection currents. So wind is high pressure, sinking air, rising or moving to replace low pressure, rising air, in what we call a convection current. So I'll say it again. Wind is high pressure, sinking air, moving to replace low pressure, rising air, and there's your convection current. Draw this. If you can't remember but two things from this slide, make sure it is that, again, the Earth, understanding that wind is because the earth is unevenly heated, causing pressure differences. And those pressure differences is why we have wind. All right, you're about to watch a video. I need you to watch that video to about 1 minute and 45 seconds and then pause. Once you pause, answer the 7 questions on your test, or no, excuse me, your notes. While you're watching the video, these are the questions I want you to think about. 1, what is the cool air doing? 2, what is the warmer air doing? 3, which direction is the cool air moving? 4, which direction is the warm air moving? 5, which warm air, cool air is the high pressure air? And 6, which is the lower pressure air? Pressure belts. So we just talked about what is wind and how it's just air traveling from the equator to the poles, air traveling from the poles to the equator. Because they're different temperatures, they have different air pressures, and because of the differences in air pressure, you get your wind. And so as air travels in many large circular patterns called convection cells, they are separated by pressure belts that include bands of high and low pressure every 30 degrees of latitude. I'm using yellow to circle what these pressure belts are called. And again, they're just large convection cells. You have your low pressure rising and your high pressure sinking. Now I know you might be a little confused by the differences in the color, but what this does a good job of showing is as that cold air sinks, and I'm on the other side over here, as that cooler air sinks, it starts to warm up. And when it gets warm, it starts to rise. And as that air rises, eventually it starts to cool off, and then it starts to sink again. Now, that is a convection cell. The combination of convection cells and the Coriolis effect produce patterns of air circulation called global winds. So you don't have to know the names of the global winds, so this part I'm going to go through pretty quickly, but there are different ones. We have your polar easterlies. They are found at 60 degrees latitude in both hemispheres. They are formed because cold sinking air is moving from the poles towards 6 degrees north and 60 degrees south. Again, that means they're moving towards the equator. These winds are responsible for bringing our cold Arctic air over the United States. Your prevailing westerlies are the wind belts found between 30 degrees and 6 degrees latitude in both hemispheres, and they're called your westerlies. They flow towards the poles from west to east. They are what are responsible for bringing our moist air to the United States. Trade winds are winds that blow from 30 degrees latitude almost to the equator. They are called trade winds. Your Coriolis effect causes the trade winds to curve west in the northern hemisphere and east in the southern hemisphere. Early traders used these winds to sail from Europe to the Americas. Then there are areas called the doldrums. Now remember we said your trade winds come almost to the equator. And so the doldrums is at the equator. This is the area where your trade winds meet. Now there's very little wind there because it's just very low pressure. And like we said, the key thing I said that if you don't remember anything about what causes wind, you got to understand wind is caused by differences in air pressure. So if it's just low pressure there, there's not a lot of difference, which means you're not going to have a lot of wind. Same thing with the horse latitude. They're found at 30 degrees north and 30 degrees south. The winds are weak in this area because they have just a lot of high pressure. Wind is caused by pressure differences, which means if it's just high pressure, then there's no difference in pressure, which means there's not going to be a lot of wind. Your jet streams are your atmospheric conveyor belts. They are narrow belts of strong winds that blow in the upper troposphere, so about 7 to 10 miles high in the atmosphere. They can reach maximum speeds about 400 kilometers per hour. They do not follow regular patterns, and they're important for pilots and meteorologists. Pilots, especially when they're flying their airplanes, because one, sometimes you need more fuel when you're going against the jet stream than you do when you're going with the jet stream. Also, as far as time, you're going to get to your destination faster if you're riding along the jet stream. You're going to get to your destination a little later if you're going against it. As far as for meteorologists, jet streams indicate a change in the air because they bring a lot of moisture and things with it. So a meteorologist will want to watch to see what does that jet stream bring along with it. The Coriolis effect. If you look at this picture, you will see that the black lines, as we discussed, air is rising at the equator. It's warm air. It's rising at the equator. Because of convection and because of how heat transfer works, that warm air at the equator is going to start traveling towards the poles. It would like to do that in the shortest, straightest path it can go, which is what's indicated in the black. This is the path that wind would like to go. It would like to go on a straight path from the equator to the poles. But that's not the path that it can take because the Earth is spinning. We're rotating on our axis. That's how we get day and night. And so because the Earth is rotating on its axis, the purple represents the curve. The wind starts to curve. Your ocean currents start to curve. They're curving because the Earth is spinning. And so your Coriolis effect is the apparent curving motion of winds and ocean currents due to Earth's rotation. Now, this slide encompasses everything that we just talked about. So here are those large convection cells. Here is all that warm air rising, cold air sinking. Here is all of that high pressure air flowing to replace that low pressure air. Here's all that energy from the equator, that thermal energy from the equator trying to travel towards the poles. Again, stressing that it can only travel so far before it gets too cold and has to sink, and how it can only travel so far before it gets too warm and has to rise. But it's still a large convection cell, which generates these purple, our global winds, our prevailing westerlies, our trade winds, our polar easterlies. And as you can see, here are your horse latitudes and your doldrums. And see how they don't have any wind near them because they are areas where pressure is the same. So there's not going to be a lot of changes. Notice again that they're also curved because of Earth's rotation. They're not going in a straight path because of that Coriolis effect.